In this video I want to show you why the focus directrix definition from the last video is equivalent to the two focus definition from a couple of videos back. And here's the way this works. Any point on the ellipse has the property that Fp is equal to whatever the eccentricity of the ellipse is times Pd, where E is between 0 and 1. Well, if I just showed you the ellipse and didn't show you the focus and directrix, because of the way the ellipse has symmetry, unlike the parabola, it's possible that the picture is sort of upside down, that directrix is really over here, and the focus is really over there. So let's just call this F1 D1 now, and call this F2. And this is, here I'll call this lowercase d1, directrix 1. This is like the other directrix. Well, it will still be true that PF is equal to PD, but this time I'll call this D2. Sorry, that FP is E times PD. So let's say F2P equals E times P D2. And since I now have 1s and 2s, let's go like that also. Now if I add these two things together, I get F1P plus F2P is equal to E PD1 plus E PD2. Factor out the E and get PD1 plus PD2. But notice PD1 and PD2 together add up to whatever D1, D2 is, which is a constant. I'll just say E D1, D2, which is constant. So that's why focus directrix definition leads us to the fact that for any point on the ellipse, the sum to the two foci is some constant. Now what constant is that? Well, it came up in another lesson that constant had to be equal to 2a. I'm not going to rederive that right now. F1p plus F2, where a is the distance from the center to the vertex. So putting these things together now, I'm going to do a little proof here. Here's the center of the ellipse. Here's the focus of the ellipse. Here's the vertex of the ellipse. This distance is C. This distance is A. Let's also have this distance from the center all the way down to the directrix. Let's just call that D. And what I want to show you is that the eccentricity has to equal C over A, which is what we had in previous lessons. I want to show you that it comes from the whole focus directrix property. That eccentricity that we did in the last video is the same eccentricity as the C over A from the other videos. And the way this works is I'm going to use this point down here, the vertex, and call it P. Call this point F, the focus. So we have the fact that Fp is equal to E, eccentricity, times P, capital D. Capital D, that's that point on the directrix down there. But Fp from here to here is actually A minus C, because here's A and here's C. So I can replace that with A minus C. And PD is from here to here. Well, that's just the same thing as here's D and here's A. So it's the same thing as D minus A. distribute that E through, ED minus EA. Now we can do one more thing here. If I come back to the common distance is 2A, which means over here, this thing, this ED1, D2, which is really the same thing as 2 lowercase d, if I'm going to call this distance d, just like I did in the other diagram. If that's equal to 2A, then I can divide both sides by 2e and get 2a over 2e equals a over e. So I'm allowed to replace the d over here with a over e. The e's cancel out. And now I have a minus c, that's all the way here on the left, is equal to a minus ea. Subtract a from both sides. Divide both sides by -1, with points up here. Get c equals ea. Divide both sides by a. Get e equals c over a. So these two definitions agree. The e, the eccentricity from the previous lesson, is the same as the eccentricity from the last lesson, and that's just a little derivation of how these two concepts, focus directrix definition of ellipse and the two foci definition of ellipse, are in agreement with each other.